Hi, my name is Matteo Farino, and in this video I will be talking about our CVPR paper MultiFlow, shifting towards task-agnostic vision language pruning. This paper focuses on pruning vision language models, which, as you surely know, are popular because they can be easily fine-tuned for various tasks. Traditionally, model pruning with VLMs relies on dynamic sparse training, where pruning occurs gradually during fine-tuning. This process has two main drawbacks. First, it requires repruning for each new task, and second, it starts retraining a dense model every time. Hence, we explore a new direction, task-agnostic vision language pruning, where the goal is to prune once and obtain a universal lottery ticket without needing any specific task details. Well, this approach faces two significant challenges: the high computational cost of pruning large vision language models, and ensuring the pruned model transfers well across diverse and unknown tasks. So let's examine the first challenge, which is fast pruning. Traditionally, pruning requires either computing gradients with respect to a known loss function, which in our setup is unavailable, or weight reconstruction, which typically relies on second-order information. However, both alternatives are pretty resource-intensive. Luckily, recent studies on LLM pruning suggest that valuable information already lies in model activations. And additionally, we observe that common saliency criteria for weight pruning typically consider only metrics that are related to the weights themselves, such as their magnitudes or gradients, and ignore structural information. So in this work, we propose that if we can quantify the importance of neurons, then the importance of weights could be determined by its connection to important neurons. So this is where the information flow score comes into play. To estimate neuron importance, we use activations. For an input neuron, this is the average of the estimated L2 norm of its activation, modulated by all attached edges, so the weights, which represents the average emitted signal by the neuron. And for output neurons, we reason symmetrically by using the average received signal. We then enhance the standard criterion for weight importance, which is weight magnitude, by incorporating the saliency of both input and output neurons connected to the weight itself. Now let's move to the second challenge of our setup, which is transferability. Indeed, while finding a universal lottery ticket is appealing, we have a core issue. The impact of removing the parameters of a specific modality may vary according to the task. So, for example, pruning some parameters from the vision encoder may have a different impact on image text retrieval than it has on image captioning. So, which modality shall we privilege when pruning? And the answer that we give in this paper is none. And the rationale is very simple. Since no prior knowledge is available on the downstream tasks, then one can assume that all modalities are equally important and allocate the same global sparsity in different modality groups. So the second core component of MultiFlow is Multimodality-Aware Compression. Instead of global pruning using the information flow score, which we just discussed, we use weight magnitude within different modality groups to determine layer-wise pruning ratios based on a global sparsity value which is consistent across all modalities. So for example, if the target sparsity is 50%, we prune 50% of the weights in both the vision and the text encoders without prioritizing one over the other. This approach essentially retains as many parameters in any layer as one would get by performing global magnitude pruning within a single modality's parameters. So the design of MultiFlow combines both speed and transferability. For each layer, we retain the top parameters with the greatest information flow score, with the pruning ratio determined by modality separation, so multimodality-aware compression. So the information flow score accounts for fast weight scoring, and the multimodality-aware compression accounts for determining the sparsity distribution of the vision language models, ensuring that all modalities are equally balanced. Here we have some experimental results. On the left, image text retrieval, where MultiFlow constantly outperforms other pruning strategies, while on the right we have image captioning and visual question answering, where MultiFlow either outperforms or matches the best performer, while having negligible compensation with respect to other strategies. Aside from major benchmarks, we also explore how different strategies for determining layer-wide pruning ratios affect the sparsity distribution, discovering a surprising phenomenon: full modality collapse. This occurs because activations and weight magnitudes vary significantly across layers and modalities, potentially leading to pruning an entire modality when pruning is done globally. And in the paper, we also explore the extreme case of 90% sparsity, a level at which VLMs typically fail to be pruned successfully, unlike classical convolutional neural networks. Here, we make a small leap towards closing this gap. So, for example, in image captioning, the BLIP score for XVLM is still greater than 30 points. So in conclusion, we explore the problem of finding a universally lottery ticket with VLMs. We introduced MultiFlow, which is specifically designed for this purpose, and results show that MultiFlow compares favorably to the state-of-the-art while being significantly lighter. And by additional analysis, we discovered that VLMs can indeed be pruned to high sparsities, and that beyond the classical layer collapse problem, pruning with VLMs can also incur in modality collapse. These are some references for this presentation, and thank you very much for listening up to here.